today we're going to be talking about complex analysis. This is going to be my first lecture in complex analysis. Today we're just going to be introducing complex numbers and what they mean. So what are the complex numbers, first of all? So the complex numbers are an addition to the real numbers. Put it simply, well, I think some historical context is appropriate first.
Yeah. If you check this try before you start.
I did. Couldn't find anything better. So, remember, the quadratic formula has been known for a very long time. So, this is the solution, of course, or the two solutions, judging by this, to the equation ax squared plus bx plus c is equal to 0. We all know that, right? But of course, you can choose some coefficients such that b squared minus 4ac is less than 0. And people didn't really know what to do with roots like that. But it wasn't that important back then, and so they ignored it. But then, one of the most underappreciated mathematicians of history, I think Girolamo Cardano, came up with a method to solve any cubic equation of the form ax cubed plus bx squared plus cx plus d is equal to 0. He now had the tools to solve any equation like this, and the formula is so complicated. But he noticed that for the majority of coefficient combinations tested, if he sketched it out, he wouldn't get 3 roots like he expected. The majority of the time, you didn't see something like this. You saw something like this. And yet, he was getting 3 possible answers instead of 1. And that's when he had to look further in the situation and realize that most of the time, whatever he plugged in was giving him a negative number under a square root. And he was forced to approach this. Well, a lot of people before him were forced to approach this problem, but they just dismissed it and moved forward. He was the only one who was actually courageous enough to work with it. And he assigned the symbol I to it. And later, because of that letter, I, and because of its connotations with pure math and only pure math, well, until it became useful in physics, it became known as an imaginary number. And despite this number arguably being the most important number in a variety of physical fields today, fluid mechanics, quantum mechanics, and electromagnetism, not to say electrodynamics, they are no longer imaginary, but the name has stuck. And we call any complex number a real number plus some imaginary number. It actually looks like the symbol for rational numbers, which is why we don't use it. So you could also say something like this. Some real number plus some real number times I, that crooked square root of 1. That's what we call a complex number. So now, why are these useful? Well, the main purpose for them was to graph them. Now, as you'll notice, this is kind of like a Cartesian product. It's like you're taking a real line, another real line, and rotating one of them. So this is Ri, you could say, or you could just call it I imaginary. So if you have a number a plus b times I, remember I is the square root of -1, then you can graph it on the complex plane. This will become very useful as we go forward. So how do you graph a plus bi? Well, it just gets transmitted to the point a comma b on a normal Cartesian plane. The real component is a, so it's on the line x is equal to a, and the imaginary component is b, so it's on the line y is equal to b. Those two, of course, only meet over here. So this is a plus bi. That's how we graph one of these on the plane. Now, what else can we do with it? How do we calculate, for example, the square root of a plus bi? Well, all of that is extremely hard to do. Well, not hard, just tedious when you have it in this form. But you can also convert it using Euler's theorem, one of many, to polar form. Now, the thing is, we'll actually have to prove this, and you might just say, well, from analysis 1, we already know that these guys have Taylor series, so this should converge. And yes, that works for real numbers, but right now, we have to show that this holds for every single complex number. And we have to justify what it means for an infinite system to converge in complex numbers yet. So that we can't make the Taylor series argument right now, thus we can't prove this yet. But we'll get to prove it eventually. For right now, just remember that this is really, really, really useful. Now without that, we can just use polar coordinates. Remember that x comma y gets transformed into r cos theta, r sine theta, in a polar transformation. And in the same way, you can write a plus bi is equal to, so z is equal to a plus bi. And by the way, the convention nowadays is not to write x for a complex number. X is usually reserved for real numbers. We call some complex variable z. So, if z is equal to a plus bi, you can also write it as r cosine theta plus r sine theta I. So now, what does this mean? What is r? What is theta? Well, remember the mappings of r and theta from regular Cartesian to polar. R is just the square root of x squared plus y squared, and theta is arctan y over x. So how does that transfer here? Well, r is equal to the square root of a squared plus b squared, and theta is equal to arctan e over a. And we have special names for these guys too. This is called the modulus. It looks like you're putting two absolute value signs right next to z. In fact, this is the exact same as taking the magnitude of a vector. And this is called the argument of z. It's just measuring, if you graph z in the complex plane, what that angle is from the real axis. Now we can suddenly take square root, because it's no longer a problem of a plus bi, it's a problem of the square root of e to the I theta, which is obviously just e to the I theta over 2. Then you have to use half angle formulas. That becomes a little bit tricky to plug in. Now, one extra thing we have to acknowledge. You might remember, well, you should remember, y equals x squared, or f of x equals x squared. We set this. What is f inverse of x? Now you might just knee-jerk say it's the square root of x. But, negative square root of x also works. These two are called branches. There's a positive branch for the positive root and a negative branch for the negative root. And you'll see this for the fourth root, for example, too. Now, the real numbers, this phenomenon doesn't happen with any odd powers, because if you cube any real number, it's going to give you the negative version of that real number cubed. But the same thing does not happen with complex numbers. You might have heard before about roots of unity, which are the solutions to the equation d to the n for integer n, positive integer n. Well, it doesn't really make much sense otherwise, because if it's wait, no. Sorry. So, yeah. But I'm getting sidetracked. So, it's the solutions to this equation. And you might say, well, depending on what n is, it's going to be either two solutions, or it's going to be one solution. But that's not how it works in complex numbers. In complex numbers, this has n solutions. And to see why, well, it's pretty hard using a plus bi, but if you use this polar form, you'll immediately understand it. So, let's say we write z as r e to the I theta. Then, we want to solve all r e to the I and theta is equal to 1. Now, the first thing we notice, this r should probably disappear. But before that, what makes this equal to 1? Because here's the thing. We need this to be equal to 1 exactly. No more, no less. Why? Because either it's 1 or it's something less than 1 with an imaginary component. And r is supposed to be real, so it's not going to be destroying that imaginary component. But do you see this? That's totally real. 1 is a real number. There's no imaginary component. Which means that e to the I and theta better have no imaginary component either, because r has no imaginary component to cancel each one out. So when does e to the I and theta have no imaginary component? Well, when sine of n theta is equal to 0. When does that happen? Well, it happens at 0, pi, 2 pi, of 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, and so on. You might not expect it, but every single solution to this equation is, oh, wait a second. I say 0 pi, 2 pi, 3 pi, 4 pi, but in reality, only some of these work, because r is always positive. So this ends up being negative 1. It's not, there's no way we can choose r to make this a solution. So when is sine equal to 0 and cosine positive? Well, at 0, 2 pi, 4 pi, 6 pi, 8 pi, just 2k pi. Which means that the solutions to this equation are going to be z to the 2k pi over n. You might say, well, that's infinite. But realize that this loops back in on itself, because in polar coordinates, 0 is effectively equivalent to 2 pi when we're talking about theta. So 2k pi over n, if k is equal to n, this becomes 2 pi, which is logically equal to z0i, which is 1 again. So, oh, sorry, I don't mean it that way. anything like this solves it, but D will look at it. Let's draw 2k pi over ni for an example on the complex plane. So let's take n equals 2 first. Z is equal to 2k pi I, which is just z to the k pi I. And now writing that out, what does that give us? Cosine k pi plus sine I sine k pi equal to 1. So, well, this is always true. Now, what values does this take? You either have k equals 1, gives you what? Cosine pi is equal to -1, and sine pi is equal to 0. So, this is a solution right here. Then you try 2, and you get cosine 2 pi plus I sine 2 pi. This goes to 0 again, and this is 1. 2 points. Interesting. Now let's try 3. So that's going to give us 2/3 k pi. 2/3 k pi. Now you plug in 1 again, and you get cosine 2 pi over 3 plus I sine 2 pi over 3. Unfortunately, my brain only works in degrees, so I have to convert it to 120. So cosine of 120 is around here, and sine of 120 is, so just something 1 unit away from the 1 unit away from the origin and 120 degrees away from the x-axis. And then you increase k by 1, you get 240 instead, and then you get 360. See, this has 3 solutions. Then you up the number to 4, and then to 5, and so on and so forth. Roots of unity form regular polygons when you draw all the vertices together, or you connect all the vertices like dots. The roots of unity have that very nice property. But that leads me to the last nasty thing I have to talk to you about today. This is always true. So now let me ask you, in complex numbers, what is the value of ln1? Now this is an impossible question to answer. It's completely impossible because ln1 is not only undefined in the real numbers, but in the complex numbers, you could literally take this to be anything and anything. This could be 2 pi times any rational number times I. ln1 cannot take on any value. But in general, ln of z has so little meaning compared to ln x. Because e to the z, or e to the iz, according to our polar definition, is exactly the same as e to the iz plus 2 pi I. Because you're rotating by an angle of 2 pi. It's literally the exact same. So, if we define f of z is equal to e to the z, we now have, or e to the iz, we now have f of z is equal to f of z plus 2 pi, which is equal to f of z minus 2024 pi. D plus any even number, pi, is the exact same as f of z. And so, what is f inverse of f of z? Is it equal to z? Is it equal to z plus 2 pi? Is it equal to z minus 2024 pi? Nobody knows. And so, this is why we have to use branch cuts. The logarithm is just the worst example of them all, but there are also plenty of other functions that act like this. But don't worry, even though complex analysis seems to be a lot more crazy in the beginning than real analysis, everything will get resolved real quickly because we're heading towards the definition of analytic function. But to get there, first we have to define continuity and differentiability in the complex numbers. And that's what we'll be doing next time. Thank you everybody for watching.